The fourth principle of molecular orbital theory states that atomic orbitals will combine to give molecular orbitals only when the atomic orbitals are of similar energy. And this principle is why we're not talking about things past neon, by the way. But anyway, here's some ideas. If you have a 1s and a 1s atomic orbitals coming together, going to give you a great molecular orbital. But a 1s atomic and a 2s atomic orbital, not going to give you very good molecular orbitals because they're so far apart from each other. They don't mix very well. Now, 2s plus 2s is great. 2s plus 2p doesn't do a good job. 2p plus 2p would be great, but 3s and 2s doesn't give very good ones, etc., etc. So we're only doing up to neon because that's 2p plus 2p, 2s plus 2s, and 1s plus 1s. When you get past neon to chlorine or bromine or iodine or any of these other ones, then you start to have lots of mixing. So like maybe 3p and 4s would start to mix, and the molecular orbitals get much more complicated, and this is where computers can really help out. So anyway, that's why we're keeping it just up to neon, and this is great examples, but realize as you get into other classes, then you may have to deal with this other kind of mixing that's going on. So here's a question. What combination of atomic orbitals would you expect to create the best molecular orbitals? And again, the punchline is you want them to be as close to each other as possible. All right. And you can see that 1s plus 2p, those aren't even close to the same. 2p plus 3p, not even close. But 3d plus 3d should give pretty good molecular orbital mixing. And this is what happens with transition metals, by the way. A 4d plus 4f isn't going to happen. 5G, which is hopefully an orbital type that's coming but isn't here yet. It needs no molecular orbitals. Well, conceivably it would. That's not a good answer either. Anyway, hopefully the idea is that if they're the same kind of orbital, they'll mix well. If they aren't the same kind, then you may have to use computers to see if they mix at all. By default, I'd say they probably wouldn't mix real well unless those n numbers are bigger. This is the molecular orbital diagram for dilithium once again, and we can now kind of understand a little bit more about what's going on. So on the left-hand side, you have lithium number 1. On the right-hand side, you have lithium number 2. And then in the middle is the actual molecular orbital diagram for the dilithium molecule. So lithium is 1s2, 2s1, and you can see those gold kind of arrows. That's what that represents on both the left and the right side. And then in the middle, we have the molecular orbitals. 2 atomic orbitals make 2 molecular orbitals. One's lower in energy, the bonding. One's higher in energy, the anti-bonding with the star. So notice we have sigma 1s followed by sigma star 1s, then sigma 2s followed by sigma star 2s. Well, the 1s electrons combine to make 2 sigma 1s and 2 sigma star 1s. And those aren't super exciting for us. However, on the top part, the 2s atomic orbitals will combine in the lower one there to make 2 molecular orbital sigma 2s orbitals. So if you want to know if this is stable or not, we can use that bond order definition, 1/2 parentheses bonding minus anti-bonding. Now all the lower ones are the bonding ones. There's 2 bonding ones there and 2 bonding ones there, so that's 4 bonding. And we also have 2 anti-bonding there, and this one is empty, so there's 0. So it's 1/2 parentheses 4 minus 2, bond order 1. This is a stable molecule. So dilithium does exist. Darn it, it doesn't run the Starship Enterprise yet, but maybe one day, you never know. But it's kind of fun for me as someone who's really into Star Trek to think about stuff like that. Diberyllium would be 2 beryllium atoms, and beryllium has 1 more electron than lithium. So beryllium is 1s2, 2s2. And if each beryllium is 1s2, 2s2, you can probably imagine that when you have an extra 2s electrons, they're going to go in the anti-bonding orbital. And so just like with dihelium, diberyllium is going to have just as many bonding as anti-bonding electrons. It's going to have a bond order of 0, so we would not expect diberyllium to exist. Draw it out if you want to. It's a totally cool exercise. But dihelium, diberyllium, probably not going to happen because they have a bond order of 0. When you get to boron, this is our first atom that we've seen with 2p orbitals. And remember, when you have a 2p orbital, or a 3p or 4p or anything like that, each of them has 3 atomic orbitals. There's like a 2px, a 2py, and a 2pz. So because we have 2 atoms coming together, they're each going to have 3 2p orbitals. That means there's going to be 6 molecular orbitals in this part. And what happens when those 6 molecular orbitals come together for the 2p, they end up making 2 sigma and 4 pi molecular orbitals. Now the sigmas, you're going to have a lower bonding sigma and a higher anti-bonding sigmas, and the pi's, you're going to make 2 lower bonding pi bonds and 2 higher anti-bonding pi bonds. So it's kind of weird. So there's a little bit more of a pattern here, but it is a pattern that can be predicted. Unfortunately, though, there's a little bit of a catch, and it depends on where you are in the periodic table where this catch becomes relevant. So in this point now, I'm going to refer to NBC, and also, as we'll see in a little bit, phone, F-O-N-E. Now, NBC refers to atoms with boron, carbon, and nitrogen, NBC. And when you have 2 atoms coming together that are NBC, they have the pi bonding ones lowest. Those are those right there, followed by bonding sigma, then followed by anti-bonding pi, and anti-bonding sigma pi. Now notice that the pi's, there's 2 of them, and sigmas only have 1. So if you go from lowest to highest, it creates what I will sometimes refer to as the 2-1-2-1 pattern. That's 2 pi's followed by 1 sigma, followed by 2 anti-bonding pi's and 1 anti-bonding sigma. This is what you'll use for molecules that have nitrogen, boron, and carbon. So for example, N2 will use this, or B2, or you could also have things like CN when the 2 atoms come together. But if you have N, B, and C molecules come together, you want to use the NBC diagram. This 2-1-2-1 is what happens when it starts to plop out. Now, the orbital diagrams become more complicated. You can start using core or core electrons in square brackets to represent the 1s interactions. And this is similar to the noble gas notation we used. So, for example, boron's atomic electron configuration is 1s2, 2s2, 2p1, but you could write that as helium in square brackets, 2s2, 2p1. If you write for molecular orbitals core or core electrons, that represents the 1s interactions, and I'll show you some examples of that here in a little bit. This is for NBC, but there's also oxygen, fluorine, and neon. So those 3 have a different thing, and I'll show you that example in a little bit. This is an example of diboron. So diboron, when you do its configuration, each boron is 1s2, 2s2, 2p1. Now notice here the core. This 1s isn't even showing because the 1s on the left and the 1s on the right will cancel each other out, so it's no big deal. So 1s2 is just shown there under core. Then we have 2s2 and 2p1. That would be the 3 electrons in the orbitals. But the right-hand side is the same. It's another 2s2, 2p1. So when you combine the atomic electrons into molecular orbitals, you can see how the sigma 2s and the sigma star 2s are canceling each other out, and that's very normal. But what's interesting is that the 2p electrons, 1 2p on the left and 1 on the right, they go into the pi 2p orbitals there, the lowest part of the 2-1-2-1 NBC interaction. So 1 electron each is going to give it some cool properties, but that is the diboron molecular orbital configuration, which is pretty cool. So the sigma 1s and sigma star 1s are both filled. Then you have sigma 2s 2, sigma star 2s 2, and pi 2p has 2 electrons inside it. There is another set of orbitals, though, as we said. There's also the oxygen, fluorine, and neon. So I'm going to refer to these as phone, F-O-N-E. And when you look at the phone orbitals, now the sigma is lowest, followed by the 2 pi bonding, and the pi star, the two of those follow, and sigma star follows that. So notice it's the bonding orbitals that flip, the anti-bonding orbitals stay the same. So while NBC had a 2 1 2 1, the phone orbitals are 1 2 2 1, sigma first followed by the two pi's, then pi star, then sigma star. So it's only the bonding orbitals that flip when you go from NBC to phone. And again, I'm just the messenger here. I know this is a little weird, but it's all stuff you can do. As before, core electrons in square brackets can represent the sigma 1s interactions, and that'll save you some time as we go through here. This is the molecular orbital diagram for dioxygen. Now again, down here on the bottom, the core electrons, that would be the 1s interactions. Oxygen, the atom, is 1s2, which isn't showing, 2s2, 2p4. So it's 1, 2, 3, 4. And the right-hand side oxygen would be the same way. 1s2 doesn't show, 2s2 does show, 2p4. So the two 2s electrons combine with the other two 2s electrons. The first two go in the sigma 2s, fills it up. Second ones go in sigma star 2s, fills it up. Good to go. But the excitement is in the upper part. And remember, it's 1, 2, 2, 1, sigma, pi, pi star, sigma star. You have a total of 4 electrons on the left and 4 electrons on the right. That's 8 electrons. So 2 of them go in sigma 2p, 3, 4, 5, 6 go into pi 2p, and finally 7 and 8 go into pi star 2p. And by the way, this is Hund's rule we're seeing. Each electron gets its own orbital first, and you only pair up if there's no more room. So in Hund's rule, notice that each electron gets its own box first. This is the molecular orbital diagram for O2. And again, it's got 1 2 2 1 instead of 2 1 2 1.